Okay. So good morning, everybody. We stopped here yesterday evening. It was a hard schedule. We were working so hard in the evening, and I think I'll go for a coffee a bit later. Yeah. So, well, we tried to extend this idea of projections when you have functional covariates. And perhaps what is the most important to understand is why 1 and 4 is equivalent. Because if you admit 4 is equivalent to 1, then for any p you apply the previous lemma we saw in finite dimension. So if you forget 1 and 2 and look only at 3 and 4, and you consider it for any p, for any fixed p, then you are just in finite dimension. Okay, is what we said. This projection scenario. You are in p dimensions, and to say that this conditional expectation is 0 is the same saying that all the projections, the conditional expectation given all the projections are 0. And yeah, this reasoning you have it for any p, no problem. So the new thing to understand is that this should be equivalent to that. But then it would be easy to understand why it works. Okay. So to go from here, it's quite clear. Remember? Oh, sorry. Maybe I forgot to say what xp is. Oh yes, I totally forgot. Yeah. So yeah. So as I said, xt, you fix some basis. Rho 1, rho 2, orthonormal basis. L2, 0, 1, let's say. And then you can always decompose your curve that is in L2. You can always decompose it in the sum of xk rho kt, where xk is random and is nothing but the integral of xt rho kt dt, and the integral takes place from 0 to 1. Okay? So this, you decompose your function in a basis, then you may define xp t to be the sum from k equal 1 to p of xk rho k t. So you cut your decomposition to p. Okay. So what I understand by this, so expectation of y given x is expectation of y, sorry, of u given x1, x2, and all the coefficients. And what I understand by this, xp is the expectation of u given x1, x2, up to xp only. Okay? So then it's clear that 1 implies 4. It's quite easy because you use again the expectation of conditional expectation when you derive. So this is also expectation of u given all the x's and given all the differentials. So in one way it's very easy. What about going the other way? Do you have an argument? What about going the other way around? From 4 to 1? What nice property has this sequence of random variables? Sorry?
Converges to
Yeah, but why? What nice property it has? It converges to what? Yes.
there. No.
This is a so-called marking here, yeah? You increase the filtration, you project on the increased filtration, you get a marking unit. If you get a marking unit, then you have convergence theorems for marking units. That converges to the projection on the union of all the sigma fields. Okay? So all the marking units are 0. You know that they converge to the expectation of u given everybody. So necessary this should be 0. Okay? So very quick marking of the argument gives you the answer. Well, it could be derived in another way, but I think this is the quickest way to see it. Because what you have is expectation of u given xp will converge to expectation of u given x in number 1, for instance. Okay? So, if we understood this, then things become life becomes quite easy. And we may go further and try to, oh yeah, maybe I can take a remark that your colleague made to me about this condition for random variable in testing problems to be bounded. If you remember last time, we had a lemma about equivalence between expectation is 0 and expectation of given all the projection is 0. And we have a second point on the bad points, on the bad betas. So when the condition expectation was not 0, it was interesting to know how many betas will give you the wrong answer. And remember that in that statement, we asked x to be bounded. It was a bit well, at some moment I asked x to be bounded. We need this for some analytic analytic functions arguments. And one may ask if this is restrictive or not. And in fact, you see, we said here if x is bounded. Yeah? And I don't know, under the whole generality, I don't know how to prove it if you don't suppose that x is bounded. But for testing purposes, saying that x is bounded is almost priceless, because you may always consider a transformation, say an x tilde, that is a one-to-one measurable transformation of your x. And then the expectation of z given x is exactly the same as the expectation of z given tx. From the testing point of view, you lose nothing. The information carried by this random vector is the same as the one carried by this random vector. And you may take t to bring your random vector on a bounded set. It's no problem. I'm not saying that at finite distance things will not change. I'm just saying that the theory, at least the asymptotic theory, and even the finite distance, I think, roughly speaking, will not change. Maybe some constants will be different when you transform your data, but the rates of convergence and things like that will not change. So this is to say that condition of this kind in testing, of course, please take care to some point when epsilon, sorry, when z is the residual of some regression. Of course, you don't have to transform your data to estimate the model. No, you don't touch the model. You estimate the model like usually. What I'm talking about is about testing. You don't touch the model for the estimation part. You estimate your residuals, and then when you build your statistic with the kernel, then you may transform your data to bring it on 0, 1, for instance. And this is exactly what I will do at the end of the presentation. I bring everything on zy, and you'll see how nice things become when you bring everything on zy. It's a kind of magic.
But then you have too many possibilities. You can do these transformations because when you do x beta, so you do first transform, then you do x beta. But there are many transforms, so you have many tests. And
exactly.
How do you choose the T transform?
I don't know. This is a very nice question. Would be a nice way to transform your data in such a way that your linear projection is even more informative than it was at the beginning. This would be a very nice question. But of course, this depends on the alternatives, because all the stake in all this stuff is to find the direction that makes your test very powerful. So a way to do it, of course, you say, okay, one linear projection is perhaps not enough to be powerful, but if you transform data previously, maybe you can become even more powerful. This is a nice question. I don't have the answer.
But even without considering a specific alternative, maybe somehow in this case can be something like uniformly more powerful by considering specific.
In testing problems, you cannot be powerful against anything. You don't have the choice. You cannot say, I will be powerful against any kind of alternative. This will not be possible. Some theoretical results.
In this case too.
In this case too. So with some transformation, you will probably improve power against some alternatives, and you will lose power against other alternatives.
That's not obvious. It's not obvious.
It's not obvious, but well, there are some deep results about testing telling you that you cannot hope have the same power, the same performance against any alternative with this type of testing. So my feeling is, I don't have results, I haven't studied this point, my feeling is that you changing your axis, you may reorient a little bit your power and you concentrate on some type of alternative, but very likely you will lose another type of alternative. Imagine that you make in such a way that your tails, you concentrate your tails in a very small interval in 0, 1, and then the projections will not make a huge difference when you do your projections. And probably you will miss alternatives that depend on the tail values of x, for instance. Just as a kind of intuition. But my feeling is that you don't have a t that makes your tests better against any type of alternative. I don't believe that. So now this was to say that for the point B in the new context, oops. For the point B in the new context, this condition with the exponential, it's a technical condition that finally is not so important, because one more time you may transform your x, and you take coordinate by coordinate, for instance. Usually these are bounded, or even if are not. So you may transform your x's in such a way that the norm is bounded, so it's not a big deal. So it's not, this type of condition is technical to derive what we want about the, now the betas became gammas, okay? Just to change. So now the betas are gamma, and to know that the set of all these gamma that gives you the wrong answer is very, very poor. So even if you pick one gamma randomly, the probability to get a bad gamma, or a gamma that will not tell you the truth, that is your under the alternative, it's 0. And this was the idea of some Spanish researchers to pick up randomly gammas on the sphere and to build statistics with gamma picked up randomly. It's a very natural idea. The problem is that in theory you may pick one and you're okay. In reality, when you pick only one, or even a small number, the power you have very few power in fact. And doing a maximum over the sphere is a much better idea. With a price, we saw that when you're doing maximum, you have a process and you look for the maximum of the process, but then you have the trick with the indicator function. And this is exactly what we will do. Okay. So. Corollary tells you that the null hypothesis is equivalent with. Right now we are doing exactly what we did previously. The only thing is just we go to L2 spheres in some sense. But what we will really use is more this finite dimension version. So we do exactly the same condition as we did for finite dimension, but we do it for any dimension, for any p. Well, you may say, all this is very nice, but how could you do it for any p? Already for one p is complicated because you look on the whole hypersphere, you maximize on the whole hypersphere. This is a hard problem. Now you say, I should do it for any p. In fact, you don't. You don't do it for any p. People using functional data, they don't decompose here up to infinity. They stop at some point. Usually very low value, like 4, 5, 6, that's all. And then, especially if the basis is well chosen, especially if the basis are the eigenfunction of the covariance operator, then people usually agree that the approximation with very few components is quite accurate. And they do not work with infinity. They do not work even with 10. They work with 3, 4, 5. And we're doing exactly the same. We put p to be 5 and look at what happens. And what we usually detect is people should be happy with it because it's exactly what they do when they estimate. Okay? So the idea then would be to check the condition like this one, but now instead of checking for one dimension, for a fixed dimension p, we have to do it for any dimension. So the idea would be to look at the test statistic. Of course, that will depend on p. P should depend on the sample size, and we allow p to grow to infinity with the sample size. That's the story. Very simple. Very simple story. So let's see what the test would be for the scalar responses. Well, the test is exactly as previously. There is no change. What changes inside? Well, for instance, when you want to code this and to implement this, the program is the same. What changes is p here. P is allowed to grow to infinity with the sample size. So if you have a sufficiently refined theory to allow this, it's exactly the same procedure. Okay? So we are going to use the same type of penalty that I hopefully right now you understood why is here, just to avoid working with maximum, just go to some initial guess that is gamma 0p. Gamma 0p now is a vector that of course is growing with the sample size, but fortunately things are working exactly the same way. Well, what is a bit more complicated perhaps is to estimate the conditional expectation of u given x. This was the sigma function. If you remember the previous slides, there was a sigma function here. Sigma square, and I gave you an exercise. You never said me if you solved it, to show that it's better to take the sigma squared estimate here to estimate the variance of the quadratic form than to take the squares of the residuals. Here, the residuals, we simplify everything. We suppose that u is observed. The residual is observed. Then introduce some error because you estimate the residual is not a very big deal if we understand how it works. So, of course, you are not happy with this if you remember what I said 2 days ago. But in functional setup, it's quite difficult to estimate the conditional variance of u given x, because x is a function. So what you could do is to say, well, I would just estimate the conditional variance of u given x1, xp. You can do this. Yeah, why not? But you can even do even simpler. It's a compromise between this extreme case where you smooth in dimension P, you just smooth in dimension 1, projecting already X on this initial gas. This is a compromise between this, which is the worst, the simplest but the worst in some sense. It will make you to lose power. And the best one that would be to put here sigma hat, the estimate of this to the square here, given the first P components. This is a kind of compromise. And in simulations we saw that this compromise helps you, because the test with this variance is powerful than the test with this variance system.
Why is it consistent?
Why is this who?
The variance estimator.
Well, what you should look at is under the null. What happens is, what really matters is what happens under the null. And under the null should be okay, because what you get here, it's exactly the variance of the Qn. Qn will be computed with probability 1 to be with gamma 0 p there. In fact, well, the question probably is I think the question is interesting. Why this should be consistent? You're talking probably about this hat here, yeah?
Just this trick. You say we need to condition on the full set, then we can condition on P of them, and then you say we can condition just on the single limits.
Yeah, under the null, one more time. Under the null, what will happen is that the theory you'll do it for this guy due to the penalty. So forget that you're in a functional setup. Your covariates now are just xi gamma 0 p. That's your covariates. So if you take alpha n sufficiently large, by the penalty argument, finally you select gamma naught, and the theory will be done for this covariance. So now you are on the real line, and everything could go easily. You are no longer in functional space if you take this. And what is funny enough is that, in fact, well, of course this will converge to some quantity, but in fact, when you apply the central limit theorem for this with gamma 0, what you really need to compute is a conditional expectation, the conditional variance of this given the axis. Well, I said at some point 2 days ago that the first theorem of Hall in '84 was not conditional, but De Jong and Guérin-Lavergne were conditional on the axis. So when you condition on the axis, imagine that here, for the moment, you have to believe that it's exactly like in the finite dimension. The gamma 0 p, replace gamma, and then you compute the conditional expectation of Qn given all the axes. What you will have is, here you have a sigma square, and here you have a sigma square. Sigma square of what? Sigma square you may take, if you look at the conditional variance, since the variables now are these ones, the sigma square of x gamma 0 p. Okay? You don't need to do more than conditioning on, because all the information of the covariance is carried by this when you take scalar products. I don't know if it's clear enough. I can say it again.
So in finite dimensional case, we also needed to estimate variance, and then I think it was
at some point I said it, but it was very fast. I said it that there is a compromise. I can put it again. At some point I said it, but it was fast. I said it very fast.
But the error was smoothing in P dimension.
Yeah. But I said it. It was not written, but I can put it back and show you. I think I see your problem. We had these two quantities, okay? And at some point I said that if you don't want to estimate in Q dimension, you may take here, well, at this stage, at this stage there is no projection. Okay? So here is no projection, so you have to estimate in Q dimension. But when you do your projections, you may, since in your Q statistic you only have I'm not sure I put it here. Let's see. Yeah. Here I said it was quite quick. You don't have to take this condition expectation. It's enough for the central limit theorem to take the condition expectation of what you want is a condition expectation of Qn gamma 0 given x1 and xn. Okay? This is what you need for the conditional, for the central limit theorem. Sorry, it's not expectation, it's the variance. So the square. Okay, under the null. And in fact, this only depends, it's exactly the same as the here was a beta. Sorry. Here was a beta. The same object, because Qn only depends on the projections, do not depend on the axis. Okay? So by this trick, you no longer have all the covariates, you only have their projections. So when you have central limit theorem, you may think that these are new covariates that are one dimension, and to compute everything just taking one dimension covariance. This is the trick.
Oh, but this is again the dimension Q, no?
Which one? This is Q. This is Q.
Yeah.
But this is 1.
Okay.
And here you condition everything. And then you go into the sum. And due to the independence, this is like...
Okay, independence.
The independence makes that you project only one variable. So finally here, what you have is sigma square of xi scalar product with beta. So finally, what you need to compute is the expectation of epsilon I given xi beta.
Then why would we do smoothing at all in Q dimensions if you don't need it, apparently?
If you don't have alternatives that are of single index type, this estimator is even better. Okay? If you have alternative of single index type, then smoothing in x beta would be the best that you can do. But if you don't have, this estimator is even smaller than the one that uses this one. So your test will be even more powerful. Please notice that there are two aspects inside. Third aspect about this variance is that under the null, it should be the conditional variance of the quadratic form. This is the first condition to get the central limit theorem. The second condition that you would like for your variance estimator is that under the alternative is as small as possible. Why? Because you want to divide by something that is small, not by something that is large. Dividing by something that is small makes your test more powerful. So for the null hypothesis, clearly you only have to compute this non-chromatic estimate. But for the alternative, this might be better because this will be smaller than this projection. So your test will be more powerful. Now, if your alternative depends only on one or one index, then this will be equivalent. But strictly speaking, this should be more powerful in finite samples because the variance is low, is smaller. Okay? So what I'm saying is, in general, under the alternative, sigma square x I will be smaller than expectation of epsilon I squared given xi b in general.
You mean in general, because in general it's not single index alternative.
Exactly.
Well, we don't know.
But you don't know. Okay? But of course, here in finite dimension you can pay a price, but when you go to functional data, maybe you don't want to pay this price. That's why at this point, I'm not talking about smoothing on all the axes. I prefer to take as a single one projection. Okay? Good.
But
Yes.
you could do here the same on dimension p, smooth, and then say also that maybe you get better power.
Yeah, but what would be more difficult if you do so is to find, to convince people that you still get this don't forget there is one condition that is needed, and maybe you will admit it very easily with finite dimension, but maybe no. Don't look at the screen. Okay. So you need this condition. Because you don't have the true sigma. You only estimate. So you need this condition of convergence. With a non-parametric smoother in finite dimensions, this would be not too much to ask. You just ask sigma squared to be bounded away from 0. The conditional variance should be bounded and bounded away from 0. And then you get this uniform convergence of the kernel estimator. Okay? Now imagine that you go with xp to the dimension going to infinity. I think you will have more difficulty to convince people that you get something like that. If you have conditions, the arguments become much more involved. You have to give some primitive conditions to persuade people that you get something like that. If you do it, no problem. But a referee will say, whoa, 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 wait a minute, how do you do it? Why this is true? Because this uniformity, you have to control many things. I don't say that it's impossible. I don't say, but conditions are more involved. So for readability of the paper, yeah, you can put it. You can put it, no problem. Let's go back. Yeah, we're here. Okay. So now, this is a variance estimator. We have at least 3 possibilities, as I said. The simple one, and you'll see that this is the only one that I know how to do it when you use functional covariance. This is a compromise and would be perhaps the most interesting but more technically involved, the one proposed by your colleague where you were doing things here, some smoothing in p dimension. So, well, these are some technical conditions, nothing very bad. About, yeah, all these things are, yeah, again, the power 11, yes, it's coming, the power 11 is coming, the same argument. Then the conditional variance should be bounded and bounded away from 0. Yeah, these are some conditions of on the density, this design conditions to not to be 0, not to be too large. Yeah, this is very, I don't know, looks very bad, but in fact they are not at all. If you just take, for instance, the Brownian motion, or the Brownian beach, this will be verified immediately.
What is the g times 0?
This one?
What is 0?
This is a set of the sphere on which you maximize. It may be interesting to take a subset of this on the sphere. Because if you take a subset, for instance, if you take a subset of the sphere, for instance, everything but some small piece of the sphere, then these conditions are easier to formulate. So from some technical reasons, in theory, maybe you have to take BP to be only a part of the sphere, to let a little bit, small piece of the sphere at any dimension. And this condition is to say that the domains are included one in the others. And this is very useful because when you look for the betas in P prime dimension, you already checked all the subdimensions because everybody is inside. So this is from the theoretical point of view, it's very useful. But it's very easy also to understand. No problem.
But does it mean for any P prime also?
Sorry?
So for any P and for any P prime?
Yes, for any P and P prime. So if you have a set P and you add some zeros to all your vectors, you get something in the P prime. That's it. Which is not absurd. It's like saying that you are adding more components to your vector. You use the one you had, and you add some more components to that. But the previous ones are in the new set. So the set are embedded in some sense, which is not absurd. Yeah, that's fine. And it's very useful for the consistency proof. Well, yeah, some technical conditions on the kernel. Yeah, strictly positive Fourier transform is again a technical condition, but most of the kernels are satisfying that. You have the bandwidth is okay, and P we take it to be very slow. There is a trade-off you'll see in a moment. Larger P is less powerful the test will be. So the interest is to take P as slow as possible. You go to infinity but slowly. Then of course you may say, yeah, but what happens in practice when your alternatives depend on very far coordinates? Well, there is no mystery. I mean, you may always find something that works bad. People are estimating functional data with 3 components, and they are very happy with that. And some referees ask me what happens if the alternatives depend on x 100. And I said, I don't know. What do you want to say? I don't know. You have to have many data and then you'll detect it. When you want to say stupid things in the referee, you can find stupid things. And they are very happy with 3 dimensions, and then you ask me what happens if you have 100 P's, P equal 100. Yeah. Sometimes you not even have 100 data. You cannot go to 100.
Why there is Fourier transform of the kernel?
Well, this is because the expectation of... There is a trick with this... the usual trick with that. Well, when you take expectation of u, I, it was, yeah, u1, u2, k, x1 minus x2 over h, then you can write this expectation u1, x1, expectation of u2, x2, and k, x1 minus x2 over h. And then you can write it as expectation of a u1 x1, a u2 x2, and then you can use t x1 minus x2. Well, let's say that you have 1 over hk here, not to forget it. And then you take the Fourier transform of k into h dt, and what you get finally, so this is no longer here by changing variables, So what you get finally is something like the integral of expectation of u x a I. Sorry. Yeah, no, it's okay. X e I to x 1. I forgot. No, that's okay. To the square, something like that. Fourier transform k th dt.
Squared, yeah.
So it's a square here.
Okay.
Because you have expectation exponential it, and then you have expectation exponential minus it. So you have the conjugate of that. Yeah, but you still have here some expectation, yeah? I think you still have here some expectation. Because you have an expectation. Okay?
Actually, I haven't understood what was the question for.
Why do you need some positivity? So then, if this is positive, you can immediately say that this is positive.
Okay.
Just simplifies
The question
things.
was why to be kernel.
Yeah.
Okay.
Why the Fourier of the kernel should be positive. So this was a simple way to check that this would be something positive.
Okay, so it's standard.
Because this is exactly the type of quantity that appears on the alternative. And this will be the leading term, and you don't want to be zero. So one way is to set it as strictly positive. It's not the only way, but it's a simple way. Except the Panechnikov, most of the kernels will satisfy that, and uniform if not, but it's not so bad.
And Panechnikov gives you?
Sorry?
Panechnikov gives you?
No, but the argument with the Fourier positive will not work, because it's not positive.
Okay.
No, Panechnikov will not give it. I think it works for any kernel. I don't have a general argument for what I need. So for positive Fourier, it's a very simple and quick argument. I think it works in more general, but yeah, exercise. So right now, let's see why. Well, now we have also the proof of why this probability should converge to 1. By the definition of the criteria with the penalty, you have that this is smaller or equal than that, by definition. Okay, because this is only a choice for gamma. Okay, this is only a choice for gamma. When you take gamma had to be gamma 0, this is 0, so it's only a choice, not more. Then, of course, you may put indicator on one side and the quadratic forms on the other side. And if your alpha n is such that this goes to 0, then you have the convergence of the probability to 1. Okay? So this is by definition the way gamma hat is defined. And then this is very simple. You only have to take care of this to be going to 0. And for this you have to understand, of course, what is the behavior of this stochastic process indexed by gamma. So if you have the behavior of this stochastic process indexed by gamma, then you'll have an idea about the order of these brackets multiplied by this factor. Okay? So it's clear that we have to study again what is the order, the rate of divergence of convergence of this process Q. So this will be done. Oh, sorry, I skipped one. Sorry, I skipped one. This is done in this lemma. You see that compared with the finite dimension case, where this factor was not here. Okay. How such type of result is obtained? Usually this type of result, and I'm trying to show you in a particular case, is obtained by concentration inequalities for family of, for processes indexed by Vapnik-Chernovinsky families. How do you say?
Chervanientis.
Chervanientis. Vapnik, sorry, I forgot the for VC families, yeah? And when you look in the VC family, in this concentration inequalities for U processes, there are some constants. And you have to check these constants. What is the dependence of these constants with respect to the complexity of the class? And for VC classes, the complexity depends on dimension P. So if you take into account the dependence of the constants on P, you come up with P3½ if you use an inequality given by Major in 2006 for your processes. Okay. So it's perhaps the most explicit inequality where the constants of the complexity of the VC constants appear very explicitly, and it's easy to use it. Of course, I put an OP, but you may get even constants like you like very much in this laboratory to have constants and not beauty. Yes?
Isn't it kind of lower?
Sorry?
Lower possible value?
No, it's upper. Lower, I don't know. For my purposes, to get this, I only need an upper bound. I don't need a lower bound. But it would be nice to solve this exercise to tell if this is lower too. It would be a very, very interesting point. I completely agree. But I don't think it's easy. Golubov said 2 days ago that he failed to find the lower bound. So probably it's not very easy. Okay, so you see the price you pay here is P to the power 3½ and quite funny, this price will be could be reduced to P, not to P to the power 3½. Well, you may say, yeah, but P you want to be logarithmic, so 3½ or 1, it's almost the same. Yeah, it's just for having some fun. Yeah. So you see that it could be reduced to P, not to be 3½. So then, due to this probability of the event that gamma hat will be gamma 0, finally the test statistic will behave, the behavior of the test statistic will be given by this one. You replace gamma by gamma 0. So then you have to go back to de Jong theorem and try to see if it works in this framework. But since this theorem was conditional on x's, and since these variables now are on the real line, of course the x's are changing with n. The law of x's are changing with n because you are changing p. So if you are changing p, you change the projection. But this does not change your results because this is the result of de Jong in some sense is to say that this quadratic form is close to normality and is n by n. Okay, so it does not matter that the law here changes, provided you satisfy the conditions. This is the idea behind. In fact, the de Jong theorem or Guérin-Lavergne theorem depends very much on the behavior of these matrices, and depends on two norms of these matrices: the spectral norm and the Frobenius norm. The spectral norm is the largest eigenvalues that you get, and the Frobenius is the square of all elements, square root of that. And you can imagine that this will not very much change when gamma will go to infinity. And under very quite mild condition, now you understand all these conditions I put on F gamma, and so these two norms that will give you the central limit theorem will be controlled in the same way as it was controlled with fixed P. Because what is very interesting here is if you make projections in P dimension or growing in dimension, finally you have random variables on the real line. So you have to go to study this matrix for xi gamma 0 p, and this is a real random variable, real line random variable. It's not. I know that here you're supposed it is deterministic. You can control it even if it's random.
Not always.
Sorry?
Not always.
Not always.
It's easiest to
Yeah. So what will happen under the alternatives? Well, exactly the same story. For any fixed alternative, you may write all these inequalities that are quite obvious. So this is the definition of Tn. Here you put this term and you subtract it. And then you drop this one. And you put this equal to 1. And finally, by simple inequalities, you get Tn is larger than this quantity minus alpha n. So, one more time, we understand that for fixed alternative, there will be a gamma tilde such that the projection of x gamma tilde remember what I said in the fundamental lemma with the projections. If the condition expectation of u given x is not 0, then you have a p, and you have many gammas on the hypersphere that will make that the condition expectation given the projection of these gammas will not be 0. So you'll find a p and a gamma tilde in Vp. And for that gamma tilde, this quantity will convert to a strictly positive constant. Inflated by this in front, this will go to infinity. So the test is consistent. Okay? Very simple trick. Well, and then the same calculations for the alternatives. And when you do the calculations for the alternatives, you understand how alpha n should grow to infinity. And now it's clear how it should grow. You have this additional condition with p. Previously it was only the logarithm here, but now you have also the p. So it should converge faster than p log n. But remember p to the power 3 alpha log n. Remember that what I said yesterday, on one side alpha n should converge sufficiently fast in order to get gamma hat equal gamma 0 under the null. But if it converges too fast, you can see it from here. If it converges too fast, sorry, if it's gamma alpha n, sorry, if alpha n is too big, then perhaps it will be harder to detect alternatives because this should be larger than a too big alpha n. So there is this trade-off we were talking yesterday about. On one hand, alpha n should be larger than p to the power 3/2 times logarithm. On the other hand, for the alternative, alpha n should be as small as possible. Now you understand why I asked p to be logarithm rate, or something like that. Because we don't want p to grow fast too. When p grows fast, alpha n should grow fast and you lose power. Okay, now I think it becomes clear, all this. It's a bit complicated. You have alpha, you have p, you have, I know, but. So the Pitman alternatives, you'll be able to detect it as soon as you verify this. But look, here is in dimension 1. The p dimension does not appear due to this trick of projection. You don't have here r squared n h to power p over 2. This is what you have if you smooth in p dimensions. You could do it. But with p growing here to infinity and h to 0, I let you imagine how Rn should be. Forget it. Even with a very small rate p, this will be very, very small. So you'll never have this condition satisfied. But with this projection trick, h is to the power 1/2. That's no problem. So this is the result on the alternatives. You may detect alternatives. Well, some technical results. Well, probably the proofs are not. This kind of conditions could be avoided at some stage. Maybe. Maybe. Things become very complicated when you get into functional spaces. So, this is Kakui. That's rather good. So, the delta function should satisfy some mild conditions of the kind you see here, no, not too much. So under the alternative, what will lead the statistic will be this term, and this will go to 0 as fast as Rn squared. So now you understand where it's coming from, all this condition on Rn. Well, I will very, very briefly show you how it works with a linear model. With a linear model, so you don't observe u, you have to estimate it as y minus a minus bx. This is a functional linear model, so you have to estimate b and a, and to pick up. Well, this is done by, let's take b hat to be some estimate of the slope. Many proposals are in the literature, no problem. And then you get this statistic with u hat instead of u. But the test is really the same as previously. Of course, if you want to recover the same type of results, the estimation error of the u should have an effect that is lower than the behavior of the statistic. So this will be a condition that you estimate u hat sufficiently accurate. And this condition will appear somewhere under this form. The norm of b hat minus b should be at least n to some power rho, and rho should be between 3/8 and 1/2. It's very much likely that this could be improved, but in the parametric case, of course, is 1/2. But in the functional case, 3/8 is not absurd, but is not extremely reasonable, neither. So there's some regularity required for b and for x in order to show a rate that is at least 3/8. For very, very regular b and very regular x, you don't get it. So something else should be done. And this is an open problem. What should be done. And why is this condition? Because otherwise, the condition on the h, there is no range that satisfies the conditions, all the conditions. So if you don't have this rate, you cannot smooth sufficiently in order to remove the effect of the error that you don't have b, you have b hat. At some point, if you remember yesterday here, we tried to develop the statistic under the alternative, and we had some terms. The model considered in theta hat minus the model considered in theta 0. And we said that this is of the order theta hat minus theta 0. And here will be beta hat minus beta, b hat minus b0. And here we said, well, this is 1 over square root n, so it's smaller than the others. It is exactly the same story here. But to make it smaller, you still have this degree of freedom given by the bandwidth. You may take the bandwidth to be fast to 0, and then you smooth out a little bit the effect of estimating b. The problem is that you cannot take very fast bandwidth because you lose the central limit theorem. So it's a range to be preserved, and if you want this range not to be empty, you should have this condition. Okay.
So this is because CLT is 1/2?
Yeah, you have two constraints on one side and the other one. So. But maybe this could be improved, I don't know. Certainly.
Yeah, the main question is how you can check this condition.
I don't think you can check it.
Or another way around, can you give an example when this condition is not fulfilled?
Yes. This is
I mean, this second set bounded conditions. I mean, it's because you just have one n and one h. How you can check the condition?
Yes, you have only one n. I agree. So this This condition, yeah, there's much work to be done. I mean, this was the first test the first time the test was proposed in this framework. It's an topic. I know nobody's perfect. Let's have a break. Here are the conditions now where Rn when you estimate, of course, are more restricted. Let's have a small break and then to finish with the last piece of work I wanted to show you.
Okay.
They had some coffee, I did not. Do you want some coffee?